The purpose of this video is to learn how to know when your DAG is complete, and once it's complete, how to use some software to decide which variables on which you want to condition in order to control confounding between your exposure and your outcome variable. So what we're going to do is we're going to go first to a website, and you can just find it by Googling it. The name is DAGitty. It's DAGitty, not two G's and one T. It's one G and two T's. And you just go to that website, and you can read about the website here. You can read about the software. And I find this is a very useful website. And you can run this software either in your browser, or you can download it and actually run it on your computer. So we're just going to run it on the browser. And you can see the developer is this individual named Johannes Textor. You can read more about that there. But let's just look at the website. So you just click here, and it looks like this. And so I want to point out a few things here. The first one is that a very useful menu is this how-to menu. And here you can learn how to do all of the functions that you need to do. Add a variable, rename it, add a connection between two variables, that's an arrow, take away a variable, etc. And then also point out how to adjust for a variable. Now they're using the term adjust. This is the same thing as condition on. So conditioning on a variable is sometimes called adjusting a variable. And over here what you have is you have a legend that tells you the different symbols they use for different kinds of variables. Here's the term we learned in the last video, ancestor. So ancestor of exposure and outcome. After you adjust a variable, it looks like this. Here's an unobserved variable. So remember, we had measured and unmeasured variables. So an unmeasured variable can also be called an unobserved variable. And we have the causal path. Remember, this was initially, we looked at the pathway from exposure to outcome. That's the causal path. And then we have this biasing path. This is a backdoor path that is unblocked. So any unblocked paths in this software program will be indicated by red lines. So to start thinking about how to use this program, let's go to the examples menu here. And they actually have some different examples of what DAGs can look like. And I want to look at this one down here, Schreier and Platt 2008. So here is a DAG, and this is a good one for us to look at to learn how the software works. So what do we have here? The exposure variable is warm-up exercises, and the outcome here is injury. So they want to know if warm-up exercises before you engage in sports can actually help to prevent injuries. And one thing we'll notice here is that their causal pathway between warm-up exercises and injury has another variable in the middle. It's called intragame proprioception. I'm not even sure what that means, but that's the variable that's in the middle of the pathway. And so the entire causal pathway moves from warm-up exercises to injury. And here we're just following the directions of the arrows. Now, one of the things we'll notice here is that all of the backdoor paths that are unblocked in this DAG are colored in red. So you can see there are lots of unblocked paths. And one of the things you'll notice is that part of the causal pathway is actually involved in at least one backdoor path. Let's see if we can figure out what it is. So the backdoor path is going this way. Well, it must be going in this direction. And I guess we can just come from here and go on around. So this arrow is involved in a backdoor path. So it's possible for arrows in the causal pathway from exposure to outcome to be involved in backdoor paths. The thing we have to remember is that we're not allowed to condition on any of the variables that are in this causal pathway from exposure to outcome. So for example, to block this backdoor path, we would not be able to condition on intragame proprioception. We'll have to use another variable in the backdoor path to block that path. Now, one of the nice things about this program is that once you've written your DAG and you believe that it's correct, what you can do is you can look over here in the upper right-hand corner. And what the program will do is it will make suggestions about different combinations of variables that if you condition on them, you will block all of the backdoor paths in your DAG. So for example, this first one says that if we block coach and fitness level, that we will be able to block all of the backdoor paths in the DAG. So let's give it a try and see if that works, coach and fitness level. So let's first try conditioning on coach. And the way we do that is we put our cursor on top of the variable that we want to condition, and then we hit the letter A. And when that happens, the color of the variable changes. And what you can also see is that the backdoor path in which this variable was a node has now changed from the red color. So what we have done is we have successfully blocked this portion of the backdoor path. Now, there are still some backdoor paths remaining. And what the program told us was that if we adjusted in addition on fitness level, that we would be able to block all of the backdoor paths in the DAG. So let's try that now and see if it works. So now I've adjusted fitness level, and you can see that all of the backdoor paths have turned away from the red color. And so we have successfully blocked all of the backdoor paths in this DAG. And so now you can see down here, this arrow is green now, and now we have green going from our exposure variable through all of the pathways to the outcome variable. And so what this means is that we can successfully control this model for all of the confounding between warm-up exercises and injury under the assumption that this causal DAG is correct. Okay, so now that we have seen the general ideas about how to use the software program, I'm going to try to use this software to create a DAG for my analysis and decide which variables I'm going to control in my model. And along the way, I'm going to find out if my model is even possible with the in-Haynes data. If I don't have the variables that I need in order to control all of the confounding between exposure and the outcome, probably I'm going to decide that it's not even worth running the model unless I can make a kind of argument that the confounding is maybe going to be quite minimal. Okay, let's give it a try. So what I'm going to do is I'm going to go to the Model tab, and I'm going to click on New Model. And so what it's going to ask me first is, what is the name of my exposure variable? So I'm going to call my exposure variable years of smoking. And so I just hit OK. And then it asks me what my outcome variable is. So I'm going to work on FEV1 to FVC ratio. This is my airway constriction measure. So it starts out and it gives me these two variables, and you can just drag and drop them, or drag them rather, and put them where you want. And so this is my causal pathway. It's highlighted in green. Now, to add new variables, you can just double-click anywhere on the screen. So if I double-click here, it's going to ask me, what's the name of my new variable? And let's say that, just to make a point here, I'm going to put inflammation into the model. Okay, I'm going to take it out in a little bit. But here we have inflammation, and this is an idea I had about one of the pathways between years of smoking and the airway constriction. So if I wanted to model this as part of the causal pathway, I have to put arrows in here. To put arrows in, you first double click where you want to start the arrow. So I double click and it becomes bold, and then you double click where you want it to end. So now I've got an arrow. And if I do that again, like this, now what you'll see is that we have two green pathways, right? So this is part of the causal pathway. So there's a pathway through inflammation from years of smoking to FEV1 to FVC, and there is some other part of the pathway that I've put in here, but I haven't given a name. Okay. Now I'm actually not going to put inflammation in here. So I'm going to click on it, and I think I hit delete. Is that how it? Yes. You just put your cursor over it and hit delete. I'm not going to name the pathways between exposure and disease. I just wanted to point out that you could do that. I'm going to keep it unnamed and just say that I believe that, you know, if everyone in the population had a lot of years of smoking compared to if everybody had no years of smoking or a small number of years of smoking, that the airway constriction measured by FE1 to FVC would be different in the population. And so I'm hypothesizing that there's a causal effect of years of smoking on FEV1 to FVC ratio. So how do you start building the DAG? Well, one way you can start is quite often when you are thinking about what variables need to go into the model, you start looking into the literature and you start finding these different risk factors for the outcome that you're looking at. And that's one of the things that I did. And I found a number of them. So I'm just going to start putting them in. That's a good way to start. Just start with all of the risk factors for your outcome. So let me double click. One of them is genetics. And so I'm going to double click and double click, and now I have an arrow. Now, one of the things that we want to do at each step is we want to indicate whether we have data for this variable or not. And so if we have data, we can just leave it like this. If we don't have data, then what we want to do is we want to make this an unobserved variable. And so the way to do that is you put your cursor over the variable, and then you hit the U button on your keyboard for unobserved. Okay, so now this is in my DAG, but it's an unobserved variable. It has a gray circle with nothing on the inside. Okay, so I'm just going to be putting all of these variables in, and one of them is occupational dust and fumes exposure. So this is one of the ones that I found in the literature. That is a risk factor for airway constriction. This one is unobserved. I don't have data on that. Another one that I found was childhood respiratory infections. Oops. And so I put that in there. This one also is unobserved. I don't have information on this one. Another one is air pollution. This is ambient air pollution, but I suppose it could also be indoor air pollution. I also don't have information on this one. Oh, I forgot to make these unobserved. This one and this one. And then what else? I found that actually height is has an effect on your FEV1 to FVC. So when they normalize the population level for these different indicators of FEV1 to FVC, one of the measures that they use is height. Another one that they use, now height I actually have data, so I'm going to leave this one as measured. Now another one that they use is race. We have data on this. Now this one is a little bit more complex conceptually. I'm going to come back to that later. For now, let's just leave it like that. Another one that they use is actually biological sex. So your biological sex will have an effect on your FEV1 to FVC ratio. This one is measured. And another one that we've seen before is that age has an effect on your FEV1 to FVC ratio. So let me sort of clean these up a little bit. Let's put this one over here. Okay, so these are the different variables that I have that go into my outcome. Now let me just make sure I haven't forgotten any here. Okay, it looks okay. So the next thing that probably you want to do is once you've got all of these risk factors for your outcome in here, you want to think about them one by one and think about if they would have any causal effect on your exposure. Okay, so for example, I think that probably age is going to have a causal effect on years of smoking, because if everyone is in the population is older, they've had more years to smoke, right? And so they will probably on average be smoking longer than young people. Now notice here that when I do that, I've actually opened a backdoor path between my outcome and my exposure, years of smoking. And so this pathway has become red. And over here, what you'll notice is now it's telling me that if I adjust for age, that I can block this pathway. All right, so let's just try it. So if I put my cursor over that and I hit the A button for adjust, let's see what happens. Now I've blocked that backdoor path, and so I'm okay. But let's leave this unadjusted for now. Let's do the adjusting at the end, because we probably will have multiple choices about what we can adjust for over here when we get to the end. Okay, so will biological sex have an effect on your years of smoking? Possibly, right? I mean, I suppose that there might be some different sex differences in terms of the rates of smoking. Maybe that has to do with different sort of cultural values around smoking for men and women. Maybe it has to do with differences in the targeting of advertising. And again here, if you're uncertain about it, if you're uncertain if sex has an effect on years of smoking, but you think it might, then you should put an arrow here. The conservative choice is to put the arrow. If we don't put an arrow here, that's a strong causal statement that we think there's just no possibility of a causal effect of sex on years of smoking. I think it's possible. Okay, now here, genetics, probably I need to be clear about what I'm talking about. I'm talking about genetics that leads to differences in airway constriction, a kind of biological effect on airway constriction, right? So would that particular aspect of genetics have an effect on the years of smoking? It might have an effect through your disease, right? So again, we talked about, if you get a disease, then if you have airway constriction, you might stop smoking. But I've constructed my years of smoking to avoid that reverse causality. So I don't think, other than that, I don't think there's going to be any effect of airway constriction genetics on years of smoking. So I'm not going to put an arrow here. Occupational dust and fumes, I don't think that those would actually lead you to smoke more or less. I'm not going to put an arrow. Same with childhood respiratory infections, although, that's maybe a little more questionable. If you had some kind of, effect of, if childhood respiratory infections made you sicker. But again, this is a kind of an effect through FEV1 to FVC. This is kind of the reverse causality. If you're already sick, then you probably won't smoke. And again, I've tried to construct my years of smoking to catch the right exposure period, so that I won't have that reverse causality. So again, I'm not going to put an arrow here. Air pollution in years of smoking, same thing. Your height in years of smoking, I don't think so. Race in years of smoking, well, possibly, right? Maybe you could have, there could be some differences in the rates of smoking in different race groups. So I'm going to go ahead and put an arrow here like that. Okay. Now I just want to spend a moment to clarify what I mean by these causal links from race to years of smoking and FEV1 to FVC. So this is a construct that you see in epidemiology studies all the time. Epidemiology studies control for race, and the idea is often this kind of causal effect on the exposure and the outcome variable. And this is actually a point of criticism for epidemiology from particularly sociologists. And the criticism is that race here seems to be treated as a kind of solidified construct, almost a biological reality, when in fact, probably it shouldn't be considered in that way. And so I just want to clarify my thinking about this, since I'm going to be posting these videos publicly. So my idea about this arrow from race to years of smoking, my concept is that this is passing through a causal chain, which includes things like experience of racial discrimination. And that experience of racial discrimination is leading to, for example, differential access to the labor market, differential access to education. And those things are leading to the social stratification of our society by race that we see, and that probably these years of smoking have a lot more to do with that socioeconomic status rather than with race itself. And so there's a kind of causal chain here, but I'm not sort of filling that in. I'm just using this arrow as a kind of a shorthand for that. Now I can make that clearer by writing all of that causal chain here. And the fact that I've got socioeconomic status inside this causal chain, actually we'll see later that probably I need to make that more explicit. But let's wait until later when that comes up, because it will raise another point. With regard to the link between race and FEV1 to FVC, this way that I've drawn it makes it seem like there is something inherent about particular race categories that leads to a difference in this biological measure of FEV1 to FVC. And one of the criticisms of this kind of idea is that it reifies the concept of race. Reify meaning that it makes it real just by the way we're constructing our idea about it. So I just want to be clear about my idea here. My idea here is that we can best think of race as an outcome of the process of racialization. So I'm going to put a variable in here called racialization and put a causal arrow there. And racialization to me means this is really the social construction of race. So this is the way a particular society groups individuals into race groups. And it also has to do with how those race groups play out in the lives of people in the society. So it might be, for example, the racialization of the economy where, within certain job categories, the distribution of individuals categorized by race does not match the overall population. Now, this is not to say that race is not a very important and real phenomenon, both in people's lives and at the population level and in society. But it's recognition that, to me, the best way to think about race in terms of causes and effects is actually as a social process rather than a biological process. Now, part of my views in this regard is the observation that if you go to different societies around the world, the concepts of the races are actually different. Now, another observation is related to genetic variability. And I've read that if you look at the race categories that are produced through processes of racialization, and you look at the amount of genetic variability within race categories and compare that to the amount of genetic variability between race categories, what you see is that, in fact, for the vast majority of the genome, maybe more than 98% of the genome, that you see really no differences between these race categories in terms of the genetic variability. And only for a very small portion of the genome, a small percentage of the loci within the genome, will you see differences in the genetic variability, in the prevalences of different single nucleotide polymorphisms, for example. And so that's another way to see that race really is not about genetics, because the vast majority of the genome actually has no association with race. But there is that very small portion of the genome that is somehow an artifact of this process of racialization. And so I want to put another variable here between race and racialization. So I'm going to take out this variable, and I'm going to call this genetics less than 2%. And I'm going to put this variable in here. And I need to rename this variable up here. This is now going to be genetics greater than 98%. And so this really encodes my concept here. Race is not something biological. It's not something genetic. The vast majority of the genetics has no link to race. And even this 2%, the arrow is going from race to genetics, not the other way around. So there's nothing about race being genetically determined here. In fact, I think it isn't. And here we can see in this concept that race is actually a consequence of racialization. And this genetic variability, which is downstream of race, is actually an artifact of this process of racialization. And it's possible that within this small amount of the genome, there are genes that are in fact important for FEV1 to FVC. So I cannot make the strong causal claim that there is no link at all between race constructs and FEV1 to FVC. And so that is why I have these arrows from race going both to years of smoking and from race to FEV1 to FVC. So I think I'm just going to leave these in my DAG to remind, and I need to mark these as unmeasured variables. So we've gone through the process now of seeing if our variables have any effect on the exposure. And so after we do this, the next thing we should do is we should begin to look at the variables we have in the DAG to see if they have any effects on each other. So there are a few here that I can think of. One might be that this genetic variability might actually go to height. There might be other kinds of effects on height from race as well. For example, through differences in nutrition, other things like that, similar to the effect on smoking. What else? Biological sex is likely to have an effect on height. Now, if I were looking at children and adults, I would have to consider whether I need an arrow from age to height, because as children grow, they get taller, of course. My population, because of the availability of the data, actually is only going to include individuals aged 20 to 79. So I think I can probably leave out that effect, although there might be some shrinking a little bit with older people, but I think that's going to be small enough. I'm just going to forget about that. So that's all I can think of at this point. So the next step is we need to consider whether there are any missing variables in this DAG. And the way to think about this is you need to think about each pair of variables in the DAG, and you need to think whether or not there are any common ancestors of those two variables. So if we looked at, for example, occupational dust and fumes and childhood respiratory infections, a common ancestor might be something like, we have a variable which is a parent of both of those variables. That would be a common ancestor. If any such variables exist, they need to be in the DAG. Now, it doesn't have to be a parent. It could be a more distant ancestor. So, for example, we could have a variable here, U2, that goes to U1, and then have another variable here, and U2 goes to U3. Something like this. So this is almost like a grandparent. You can think of it that way, of both of these, right? So this would be a common ancestor of both of these variables. So this one would have to be inside the DAG. Now, we wouldn't necessarily have to have these two variables in the DAG. In fact, we could probably get rid of these two and just draw the grandparent as if it was a parent. So one way to think about this is to look at your variables and think about, are there any variables here that you would expect to be associated with each other in your population? As you move through the individuals in your data set who represent the population, would you expect to see any patterns between any of the variables? Well, for me, actually, these three variables over here, occupational dust and fumes, childhood respiratory infections, and air pollution, I would expect these maybe to cluster in the population, that individuals who had one of these would have a higher probability of having the other ones than would individuals who didn't have one of these. And so for this one seems to me to be kind of a cluster by socioeconomic status. So I'm going to add a variable in here. I'm just going to call it SES, socioeconomic status. And I think that socioeconomic status would be a common parent for all of these. That if you are in a lower socioeconomic status group, that you would probably have higher probability of being exposed to air pollution, more higher probability to have had childhood respiratory infections, and a higher probability to be in occupation where you are exposed to dust or fumes. Now, here's a situation where I've created multiple paths between a variable and another variable. And so here we need to think about whether I want to make the strong causal claim that all of the effects of socioeconomic status on FEV1 to FVC pass through occupational exposures to dust and fumes, childhood respiratory infections, and air pollution. And I don't think I'm ready to say that. I think that there could be other effects on SES, maybe that I can't think of. And so I'm going to put another arrow here without any terms on it, basically just to encode all of those other things that I think I can't think of, but that I think they might exist. I'm not willing to make the strong causal claim that there is no such causal effect. Now, here's another thing that you need to think about. I've put this variable SES in here. And so I need to think about, does this variable show up anywhere in the causal pathways between other variables in my DAG? And I'm reminded that when I talked about my concept of how race is associated, or how race is a cause of years of smoking, I had this idea that it was going through a link of socioeconomic status. And so because I have that concept in here, it's embedded in this arrow, I need to make that link with this variable over here explicit. And so what I'm going to have to do is, it's going to get messy here. I'm going to bring this SES over here, and I'm actually going to break this link between race and smoking, and I'm going to put it through SES and years of smoking. But now I've made a kind of strong causal claim that all of the effects of race on years of smoking are going through SES, and I'm not actually quite sure that I'm going to want to make that strong causal claim, so I'm going to actually put this arrow back in to encode that idea that there might be other links between race and years of smoking other than what's passing through SES. And the DAG is getting really kind of messy. Maybe if I put it down here, that'll be the best. Can move this up a little bit. And you can see this is why it's so great to use this program, because if you were trying to do this on paper, it would be quite difficult. Okay, let me think. Are there any other things here that I need to put into the DAG? Well, one other that I can think of, which is possible, is that I've seen in data before that there actually is a link, an association anyways, between socioeconomic status and height. People of lower socioeconomic status on average are a little bit shorter than people of high socioeconomic status. And that might be related, for example, to differences in quality of nutrition. So I'm not sure about that, but since I'm not willing to make a strong causal claim that there is no such causal association, I'm going to go ahead and put that arrow in between socioeconomic status and height. So I think that this is complete. This is all I can think of. And so if I'm calling this a complete DAG, it means that all of the arrows that should be there are there. Any arrows that are missing are strong causal claims that there are no links, causal links between those variables. And I'm saying that for all of these variables, if I were to take any pair of variables, there are no missing common ancestors of any of these variables. Now, if you can think of some variables that I forgot, that maybe you can tell me during class time and I'll update my DAG. But I think that I'm going to go with this DAG for now because this is all that I can think of. So now I am ready to use the program to see what variables I need to condition in order to control for confounding between my exposure and outcome. And so I come over here, and it turns out that I have only one choice. Sometimes you'll have more than one choice, but I have only one choice. I need to condition on age on race, on socioeconomic status, and on sex. And fortunately, I have all 4 of those variables in my data set. And let's go over here and see if conditioning on these 4 variables actually blocks all of these multiple backdoor paths that I have. And you can see all of them are in red. There are backdoor paths all over the place. So let me start here. So I put the cursor over the variable. I hit A for adjust. And you can see that when I adjust for those 4 variables, all of the backdoor paths change from the red color. And so what this means is that if my causal DAG is correct, then adjusting for age, race, SES, and sex will actually remove the confounding between the exposure of years of smoking and the outcome of the FEV1 to FVC ratio. Now, I was fortunate to have the variables in the NHANES dataset that I need to control for confounding in the model that I want to do. Now, you might find that you don't have all of the variables that you need. And in most cases, when we're unable to control for confounding based upon the ideas of our DAG, we usually choose not to do that kind of analysis. We usually consider that to be an inappropriate selection of a cause and effect to model with the data set. Now, there might be some rare situations where the amount of confounding that we would expect in the association between exposure and disease would be very small. Most of the time, we don't really have a good way to determine how big it would be. Or maybe more likely, we would have an idea that, you know, if this causal DAG was correct, we would have confounding in the association between exposure and disease, and there's no way to control for it. But in fact, the probability that this causal DAG is true is quite low, and in fact, a different DAG is probably more likely true. We might go ahead and, you know, do that model based upon the alternate causal DAG in which we can control for confounding. So we'll just look at your chosen models one by one, and we'll make a decision about whether or not it's appropriate for the NHANES data. Now, I want to make one more point, which is related to this genetics 98% here. This is the only variable that's related to the outcome that isn't connected to any other variable. And when people start modeling, they often have the idea that you need to include every variable in your model that is a cause of your outcome. And so they start worrying, like, my goodness, I can find so many different risk factors for my disease in the literature. How am I ever going to fit all of those risk factors into my model? Or they think, many of those risk factors aren't in my data set. How can I possibly model this phenomenon without information on those risk factors for the disease? And the error in that kind of thinking is that it's not the risk factors for the disease, it's not even the causes of the disease that we need to model. We need to be thinking about if they're connected to backdoor paths, and if there's any single node on all of the backdoor paths that we can block by conditioning on the variable. Now, another thing you can see is I have so many variables in my model, occupational dust and fumes, childhood respiratory infections, that were not used in my final model. And it wasn't a problem because the backdoor paths in which they're involved can be blocked by a different variable on the backdoor path. So socioeconomic status blocked multiple paths here, and sex and age and race. If I block these 4 nodes, then I block all of the backdoor paths. So that allows me to have a model that is not confounded. Okay, now you have all of the theory and method that you need to create a DAG for your own model. And the theory and method are actually not very difficult. What you're going to find is that once you have a DAG, the process is actually quite simple. The hardest part actually is constructing the DAG. You will probably find that it pushes you to clarify ideas that you didn't even realize were a little bit murky. I think the way that DAGs push us to clarify our ideas is actually one of the great benefits of DAGs. So you should remember that you are aiming for a complete DAG that will have several characteristics. The first is that it's going to have all of the necessary arrows in the DAG. And you should remember that any absent arrows between two variables represents a strong causal claim that there is no cause and effect relationship between those two variables. And you should remember that for a DAG to be complete, there can be no missing common ancestors of any pairs of variables at the DAG. And it doesn't matter if the variables in the DAG are measured or unmeasured, and it doesn't matter if the ancestors are measured or unmeasured. Now you can follow the step-by-step procedure that I used when I was building my DAG. And I started by putting my exposure and outcome variables. Now I only had one path between exposure and disease, but you might have multiple paths through which exposure has a causal effect on your disease variable. The next thing I did was to place all of the causes of my outcome. And I found this by looking into the literature for risk factors for my disease. Now you should know that not all risk factors in the literature are actually causes of the outcome. Sometimes you might have a risk factor which is, for example, associated with the outcome because they have a common ancestor. So you should think about it carefully before you put them into your DAG. And once you've done that, you should think, do any of those causes of your outcome also cause your exposure variable? And then once you've finished that, you can begin looking at all the pairs of variables in your DAG and see if there are any missing arrows there. And finally, you can then begin thinking about any of the missing common ancestors for any pairs of variables that are in your DAG. Now, if you add any new variables to your DAG through this process, you should also think about the cause and effect relationships of those variables to all of the other variables remaining in your DAG. Once you have your best complete DAG, then you can use the software to find out which variables you can condition to control confounding between exposure and disease. So that is the process, and now you're ready. So good luck with your model building, and I hope you enjoy the process.